Hi everyone, welcome to another session of our Ask Me Anything monthly webinars. My name is Itamar, I'm the CTO and founder of Big Data Boutique, and we are in another session today where the topic is Elasticsearch and specifically modern full-text search with Elasticsearch. Today we'll talk about how full-text search is currently being done in companies, how Elasticsearch is being used for that, and how you can leverage that yourself. And we'll have a look at into the future on the technologies and methodologies that are currently being experimented and used in some places, and very interesting techniques. So about us, if you don't know us by now, we are Big Data Boutique. We are a group of experts in the world of big data and cloud. We help our customers from startups to enterprise organizations to succeed in big data projects. That basically means that we come in and help them architecture their systems that they can survive or again succeed in big data stacks. So a lot of data. We come in and bring them the right technologies, and we help them use the technologies in the right way. And there's plenty of ways to reach out to us. It's listed now on the screen. We have a blog. There is this Ask Me Anything AMA sessions history that you can browse and look for previous videos, previous sessions that we've had. And we'll be happy to hear your voice here as well in the session today. Feel free to leave us any questions or remarks either privately via Twitter or email, or even in the chat window in YouTube where we broadcast this right now. Just before we start, I just wanted to highlight what Elasticsearch is. If you're here watching this, you probably know what Elasticsearch is. Most likely you are a user to some extent already. But just to put this out there, so Elasticsearch is essentially a search server. It was built for full-text search, and by full-text search I mean the ability to locate documents with possibly even large bodies of text using a single word or a phrase or just some very specific query, possibly even in human language. So not anything that is too particular. And there are specific technologies that are meant to be used that way. Lucene is a Java library that was built years ago, and Elasticsearch essentially takes Lucene and makes it a server software. So it allows to have a distributed document-oriented data store, a search server that allows to make a lot of text searchable, and that provides it with low latency queries. And over time, it also started offering a lot more functionality, like geospatial queries and other types of queries. Some of them we will even talk about today. Funny how things went, but essentially today, we estimate that most users, like 80% of users, are using Elasticsearch, actually not for full-text search, but for centralized logging and real-time BI. So more on the aggregation and analytics side of use cases. But in the origins of Elasticsearch are in the full-text search area, and that is what we're going to focus on today. So, like I mentioned, we are Big Data Boutique, and we are the world's leading Elasticsearch experts. We provide the consultancy services, hands-on development services, and even production support with SLA. And we support many customers, many even big and known names in their Elasticsearch journey. And again, we'll be happy to hear from you if you think that you could benefit from our services and our knowledge and expertise. For today, we are going to focus, like I said, on full-text search. And we'll start really simple, but just talking about what full-text search is, how it works, on a very basic level. Those Ask Me Anything sessions are meant to be precise and to the point and not too long. We'll talk about normalization and the languages, how you treat different human languages when it comes to full-text search and Elasticsearch, and challenges like using synonyms and things like that. And like I said, we'll look at things that you will usually see and experience while going in that journey. So various challenges and pitfalls that you'll experience, and the ways to overcome them. And again, very high level in a very short manner. And then I'll start showing you some things and some patterns that we see and how you would usually act on solving those issues and challenges. And then the the bleeding edge of technology and of tooling that exists today, and it will allow you to take whatever you're doing with Elasticsearch and full-text search to the next level, and hopefully you'll find this helpful. In the end of the session, in the end of my lecture, in about 20 minutes from now, we'll open for questions, and if anyone joining us live is welcome to post any questions. You can use the chat window here on the YouTube video stream, or you can just approach us privately, and then I'll see those questions, and I could answer them as well. Of course, you are welcome to also approach us offline, or if you're watching this after the fact. All right, so let's begin. Full-text search essentially is the practice of allowing to find unstructured data using some words or some text. So usually you will use full-text search when you want to find documents or texts that are not entirely structured or not structured at all. And those documents, it's actually a practice that you're probably doing daily. When you go to Google and just put some query in it, you are not specifying whether those terms that you're looking for should be in a title or in the description field, or it's a price or it's a location. You don't do any of that. You just put your query and Google knows what to do, right? So we cannot use Google all the time. Sometimes we need to build a search experience for our users on our internal data, and for security reasons and for whatever other reason, and therefore we need to build that kind of thing ourselves. So search being the lookup of structured data or unstructured data in unstructured data, there are a couple of things that you will be doing right out of the box. Just simple keyword search, just typing a word, and it will be found. It will find the documents that contain that word. That's typical standard keyword search, and that is something that you'll definitely do, and it will be very easy for you to do. But what happens when you want to find not exact matches, what we often call fuzziness? So fuzzy queries, those kind of queries that whether you write Danny with double N or just one N, or with an I or with a Y, or you want to find parts of a word, so prefixes, suffixes, using wildcards and things like that. Or for those use cases when you want to find only the documents that contain an actual exact phrase, so those two words together and not apart. What happens when you want to find documents that are contain a specific word either in the plural or singular form, so take into account the language and the morphology of the language. Or you want to execute a search that takes into account synonyms of the words that you're looking for. So all of those are challenges that are come to your step door really fast. I mean, once you start developing a search experience and a search UI and a search backend, a search service, you'll start simple with simple keyword search, and then quite immediately all of those, or at least some of those features and feature requests are going to come knocking on your door, and you'd have to think on how to implement them. So again, it's way too broad a topic to cover everything, but I'll try to give you an idea on how to approach those. And of course, a lot of features around that, how to make sure that your search results are actually relevant and are actually sorted in the right order. And features like highlighting and did you mean and auto corrections and autocomplete. So all of those features are features that you'll definitely meet. And today I want us to focus on getting search and relevance right. And this is what we are going to do today. So if you are even a little bit familiar with search engines, you probably know what the inverted index is and how search works. So we'll not get too much into that. I just want to highlight one very important feature or mechanism within Elasticsearch and essentially Lucene that takes care of all the indexing and all the preparation of the data that goes into the inverted index, and then again on the query side, and that will be the analysis chain. So you probably know those as analyzers, and those are the mechanisms and objects that you will be defining, and if you haven't defined, then there is a default one that's being used, and those will take the text that you index and break it apart into tokens and put it into the index and make it ready for search. And again, on the search side, when you write your query, it will meet that analysis chain, that analyzer, and do the same. So an analyzer in the analysis chain is actually made up of two parts. So the tokenization, the algorithm, if you will, that will take your text, break it into tokens, and then those tokens eventually, after a second phase of filtering, will get into the inverted index. The way that you do tokenization and what filters you use, all of that essentially dictates how efficient and effective your full-text search system is going to be. It's a full art on doing this correctly, but I'll show you a couple of things that will make this work better for you, perhaps. And again, it is all going to be very dependent on the language of the text that you're handling and the use case and your user requirements and things like that. So there is no one size fits all. There's no right answer. There are just guidelines and ways on making sure that you are at least on the right way. And we'll discuss that in a bit again. So when you start writing, again, a search service, and you'll get to a point where you actually have indexed everything is in Lucene, using the right mapping and using the right analyzers and all of that, you'll get to the point where you sit down and start writing the search query itself, given the user query. So let's say the user searches for the words black phone, or it just searches for black phone and types in the search box black phone. When you start naively, you'll probably just write black phone, search on all the fields, get some results back, but then you'll suddenly start seeing a lot of results that are too good, too bad, and the order is not right, and you get some garbage results and things like that. So what will happen by default, for example, is that when you search for a black phone, you'll get black phones, but also a lot of the results with the word black, and there are other results with the word phone. Sometimes the results will have both black and phone, but not together. So you'll do some iterations, and you'll get to the understanding that you need to boost up certain fields like the title, and you need to boost also other fields, but less. Some fields you don't boost at all, like the description field. And then also you'll understand that you probably get to the understanding that you need to use phrase matches. So only show results or boost results higher if they contain the words black phone together. And then you realize that sometimes the fields are written in a bit different order, so you also want to allow for a slop, so for the words being close together but not entirely one after another, so you'll introduce the slop. And then you'll probably also start adding a couple of more features like that, and you'll end up like, for example, fuzziness, so allowing maybe a way to accept some differences in spelling, so those kind of things, and eventually you'll end up having quite a sophisticated query. And then once you're happy and deployed and everything looks okay, suddenly product comes knocking on your door and asking for a change, or give you some file some issue on some result that isn't ranking well, and now every change that you make will ruin everything that you were successfully have done before. So how are you going to deal with that? So a typical search query will indeed definitely look something like that, again depending on use cases and things like that, but it's definitely going to go that way. And then comes the question, what do we do next? So you probably, at this point when the search is going well, and let's assume that you don't need to change anything, you would now want to start and improving what we call the recall. So making sure that there are no results that you should have found but you haven't found. You do this usually by introducing things like synonyms and a couple of more things like that. And then again, it sounds simple, starts simple, but it gets very complicated very fast. For example, you would want to probably try to search for a plane and also find results that contain the words aircraft and airliner, because it's pretty much the same. However, if you think of that, and there's so many examples for this case, if you think about that, the exact word being used is very, very, very dependent on context. So probably pilots will search for an airliner, but if you want to look for just a drawing of a plane, maybe plane would be a better word. And there's, again, plenty of examples like that. There are multiple words that are synonymous to one another, but are not exactly one another for a reason. And sometimes that reason is important, and it's important to remember that. So synonyms are, again, highly subjective. Sometimes you will think that something is a synonym, but it's not really that. Sometimes, again, you would want to search for, we don't call this synonyms exactly, it's more like of an ontology. So finding something that relates to something. So if you search for Phil Collins, you probably refer to, or will be interested in finding results that relate to the band that he played with, Genesis, back in the day. Maybe not, right? And sometimes synonyms will be bidirectional, so one word will map to another and vice versa, but sometimes it's only going to be in one direction. And it's not always the case that it's going to always be true in that case. Synonyms that are not single words, like for example, Black Widow is indeed a spider, right? And if you detect that phrase, Black Widow, and you basically treat that as an entity, you definitely don't want to search for Black and Widow separately and only in the phrase way. So there's plenty of things that you could do, and I just listed this here just to give you some food for thought, but it gets very complicated very fast. Don't assume just introducing synonyms is going to solve all your problems and make search better, because it will most likely make your precision, what we call precision, and we'll talk about that in just a minute. It will make it just it will bring up a lot of results that are probably not going to help your cause. I'll just mention in this case is where we often recommend start using something like a knowledge graph that is specific to your use case or specific to the corpus that you're allowing search on. And there's a lot of work to be done there, but what I'm saying is some things are going to sound simple but will not be simple, and it will definitely help if there will be a way to measure any changes that you're going to make to your search. Another thing that people tend to forget is that search essentially is very, very, again, subjective. It's very contextual, and the intent and context of words where they appear has a lot of effect. And we'll get back to that in just a bit. But for example, searching for Python, us developers will probably not mean the snake, it will mean the language. But a lot of other people will never will never expect to get a software programming language when they search for an animal. Likewise, orange, it can be a color, it can be a fruit, and it also can be a company. And in this case, when someone searches for our oranges, do you show them the, let's say the orange the company, because oranges will map to orange, plural will map to singular? Do you show them that? You probably don't want to show them orange, the company, when someone search for oranges. But how do you do that? If you're familiar enough with how stemming works, you'll probably understand the issue that I'm raising here. So let's talk a bit about how basically those things are going to be measured. So we usually measure two things that are called precision and recall. Precision is the percentage of documents that are in the result set, have been returned as the result set, but are indeed relevant. So someone said, yes, those are good results. So the good results versus the bad results, or the not good results, are what we call the precision, usually measured between 0 and 1, so some sort of a percentage. And that value, the higher it is, the less complaints you'll hear from users. Recall, on the other hand, is the measure that measures the number of results, the number of good results that you haven't brought up in the search results. That is usually going to be a business problem, right? Because some results are actually good, but for some reason you or the search engine that you use decided not to bring them up. The user maybe will know that there is a result that he's not finding, but usually the business is going to notice that, and that is going to be a case for in the case that the business is going to ask for a fix. Now, measuring precision is very easy. I mean, leave aside the fact that precision is pretty much subjective. There could be, and there will be, and there have been a lot of arguments about whether a result is actually a good result. Some will think it is, some will think it will not. It will probably, people will probably agree on the reason why a result came up for a specific search query, but they will probably not agree on whether it's good, it's there in some corner cases. But it's very easy to measure that. So if we drop the subjectivity aside, for example, by having 3 people judge and just going with the more people with the actual opinion of the more people there. So recall is actually very hard to impossible to measure. So the only real way of measuring recall is in a sandbox, in a place where you know all the documents, and you definitely know whether for each search query, search term, whether or not a specific document is a good result or not. Again, leaving subjectivity aside, only then you can actually measure recall in an exact way. So it's not really easy to measure that. Sorry, there are ways you can actually try to get to a number of for that. So, but usually what you'll do is measure precision and try to improve on precision. But while doing that, you'll try your best on making sure that you're not damaging recall. And Synonyms, for example, is a great example for a case where you'll be maybe helping precision. And I'm saying maybe because a lot of times it will also damage precision. It will definitely damage precision in some cases, but you are going to definitely improve recall because you have now broadened the search. You've included a lot more terms, and those terms are supposed to help you find documents that you haven't found before. again, because you didn't use the right terms. So I want you to remember those two measures, precision and recall. And then after we have decided booleanly whether the 10 results that we got are good or not, there is this measure that's called relevance. And relevance is a soft measure, and it's basically just saying out of the 10 good results, let's say precision is in 100%. We got 10 good results. Those 10 good results, are they sorted in the right way? So is the first result really the best result, and then going in descending order? Yes, no. Again, very subjective, but that is also something we will want to measure anyway. And then once we have a way to measure that, we will want to try to improve it. So getting an understanding of what's going on in the system, making a change, and then seeing whether there is an improvement or not. So in an e-commerce, a conversion rate would be a good measure, or a good testimony to what really is going on in the system. You'll probably want to have judgment lists. I'll talk about this in the next slide. Or you want to start capturing click streams, seeing how people are behaving. So this is like some sort of a behavioral analysis, how people are behaving in your website. Search for something, then what they did. Did they scroll? Did they click? And what did they do after they click? You should definitely look up what's called click models. There is a lot of there are several models that try to understand what is the right behavior, because if I clicked on 3 results, do I consider all 3 results or only the last result that I clicked on? Because I didn't have to, if the first result would have been good, I wouldn't have clicked the other 2. So it's a whole topic on its own. And then again, looking at search logs and trying to make some understandings based on that. So I mentioned judgment lists. I need to have some way to understand whether a result is good or bad. I can try doing that in large scale using click models and search logs and things like that. In some after having enough data, I will probably be right, or around the area of being right. There is no replacement for human beings actually sitting down. So business experts, domain experts, actually sitting down and just rating those results. So there is a query. In this case, there is products that you see. There is Hebrew query executing on that. Again, we like complicating things. And then for that query, there are 7,000 results. And out of those first 10, 20 results, we ask a domain expert to decide whether this result is good or not. And then if all of those results are good, we can also reflect that the current search that has been executed for this user input is actually good. It has a score of 100. So this is just one tool. This tool is called Cupid. This is just one tool out of many that there are. So there's RRE and there's Cupid and there's plenty more. And there's also home-baked solutions and tools. And those are things that you definitely want to have, so you can measure, and you can even you can start understanding what's going on, and then of course have some way to do regression testing or A/B testing, and making sure that any change that you make in the future is going to help your cause and not damage it. Let's talk a bit about, once you have those judgments and decision-making processes and ways to check whether you're doing the right thing or not, let's talk a bit about how you are actually going to improve on that. So you can do this manually, of course, and you can do a lot of testing manually, but I just wanted to put it out there. There are automated tools, machine learning methods that makes things a lot simpler. And one of them is probably the most well-known one is learning to rank, LTR. So LTR is it requires you to have a way to understand, to have judgments and to see how things are getting better or not, and how people are behaving given the search results that you have, that you provide them. And given those judgments and a base query, so you develop your query, you have this query, it's running, it provides a result of some quality. And then what learning to rank gives you is the ability to look at the actual results and the actual behavior of people or people using your system on those search results, and understand from that what is good, what is working, and what is not. So the idea is that you are using your query and you're building a model offline, and then you push the model that you've built into the search engine, in this case Elasticsearch. And then once the query is finished running, it has some results, and those results are scored. You're going to run the model on the top, let's say, N docs, usually done on the top 100, top 200 documents. And out of that, it will probably shuffle those documents a bit, and it will make sure that the top results are actually results that are more likely to be clicked and more likely to be relevant and interesting to the people, to the person executed it. And again, it should definitely be an iterative process, because again, it's a machine learning, it's an algorithm, it's a method that relies on on seeing good result sets and learning from mistakes. So learning to rank is definitely something to look for, but that is like floor 10 of any search process. So after getting to a point where you have judgments and you have iterated a bit on that and you have a good understanding of what's going on and you have a good base query, then you can start integrating things like learning to rank. Let's talk a bit about what actually is going on in search. So we mentioned that very briefly, and I assume you know what TFIDF means, and that is basically the way that most search engines that we use today are actually working, and that is basically a search that scores results or decides whether a document is similar to the query that you typed. This is how it works, using what we often call an aboutness. So if I type 2 or 3 words, what is actually going on is an algorithm that is a TFIDF, that's what we call it, TF frequency divided by the document frequency of those terms, and the overall frequency of those terms in all of the documents. And that is basically what we call a bag of words, because we are going to find all the documents that contain significant mentions of the words from the query, and will float them up in the result set. And that is basically how it works. And essentially, this is going to be this is often considered to be a vector problem, right? So it is some sort of a sparse vector that has a very, very, very high dimension. So a lot of numbers in it, and basically each and those dimensions represent the number of terms and the number of words that exist. Most will have zeros, but those that are not a zero will contain the number that represents the frequency of that and the importance of that term. So essentially, if you take the vector of the query and the vector that represents the document, and then you're going to do a dot product of them, then you're going to get the document relevance score, and that is equivalent to what we call the TF-IDF formula. And again, there's several implementation of TF-IDF. Currently, BM25 is the one being used, and that is probably the most straightforward approach to do similarity search. And it works well. And like I mentioned, there is plenty of ways to measure that and to improve that. And that is traditional relevance engineering, search relevance engineering. That is what you'll be doing. But I do want to show that as a vector problem because of where things are now headed in the search world. Before I jump into the future, I just wanted to highlight one extra thing. So I mentioned that a lot of the search problem is made very hard, mainly because of the contextual, or the context of the words and the intent of the people and things like that. So if you think about that, all of the search problems are being solved by just looking at a word without considering the context. It doesn't matter whether a word came with another word or not. We will just measure the frequency of the word, and that would be the aboutness of the document. There is this concept that's called word embeddings, and word embeddings is a way of us saying, well, let's have a look for a second. Given the word, let's say Amazon, let's say which words usually appeared in the area of that word. So it could be in the paragraph where it was mentioned or in the document in general. So let's look at the top frequent words and the most frequently, the words that most frequently appear in those documents where Amazon is being mentioned or Amazon is the topic. And what you'll see here is basically some processing of word embeddings, and it also includes some an over time view of that. So you can also see some evolution, but what you see here is that Amazon before the internet has been a forest, and people knew it by a forest, and then over time people knew it as a retailer, and then after that as a company that also competes on content and on video and things like that. And that also is true and the same for other words that you see here. For persons, so Obama and Trump, again, he was a businessman and now he's the president. And Obama, the same. He was a student and then he became a statesman. So all of that is just showing you that a word has a lot of context. And in this case, you can also see how the context evolves over time. And that has tremendous effects on how we treat and how we should treat the search problem. And that brings me to where we are today with search. So advanced search systems will start treating the search problem using word embeddings, and it will look at the search problem as a vector space problem, like we've done before, but sparse vectors are the representation that is equivalent to what we do now, the TFIDF. Dense vectors are a way for us to represent those word embeddings, those contexts for specific words that we're going to run and search for. And that actually defines a problem in a different way, and it actually works very well. So now you can search for something and find documents that contain that topic without even mentioning the same name. And that is very, very, very important. So we are going to take surrounding words into account, and we are going to take essentially synonyms of those words without even mentioning that, without doing anything, but by using ways of structuring dense vectors, for example, word2vec. And there's plenty of other algorithms like that. And that will generate vectors that are dense, but they are much, much, much smaller in size than what sparse vectors would have been. And then the search will just essentially be executing a nearest neighbor algorithms, because we are going to have a lot of vectors, and those vectors each is going to basically point to another direction, but in a very high dimensional space. And essentially finding similar documents or finding documents that are similar to a query will essentially be just a matter of finding the vectors that are pointing to the same direction. Now, this is where we are today. So bleeding edge search systems, this is what they do in one way or another. Where the future is heading is, we may have heard of BERT, and where the future is heading is having dense vectors. So basically solving the problem of search exactly like I described it now, but having the dense vectors be much more detailed. And that is what BERT, and there's several other approaches like that, but this is a deep learning solution to the problem. Google developed BERT. I link to the actual paper and blog post in this slide. Google developed BERT for NLP purposes, and basically BERT is able to predict what should be the right word if you've the next word if you've written those words up until now. So this is a deep learning based language model, and it was developed for NLP purposes, but it can also be used for search. And Google is claiming that it is sometimes very helpful in improving searches. One out of 10 searches is going to benefit from executing the model that BERT outputs. And BERT, because it's a deep learning model, it is going to work with tensors, with very high dimension vectors within it. So it is something that is working in theory, working in reality, but it's not commodity. It's not something that you can take now and use. But I wanted to put it out there because work is being done to try and make those the sizes of those tensors, of those dense vectors that are being generated and worked with by BERT and models like BERT, so transformers. So work is being done to actually shrink them and make them workable, and not having each document gigabyte in sizes and more. So short documents will be gigabytes in sizes, and that's not something we can actually work with. And that is also the reason why the actual algorithm is not going to be the nearest neighbor algorithm, but an approximation of that, again, because of the huge scale of that. Now, obviously, 10, 20 years from now, computers and hardware will be so efficient that it will not be a problem, or it will be a smaller problem. But for now, this is a very big problem. So BERT is where the future is headed, right? So taking that concept of vectors and dense vectors and maximizing it to an effect. So just to sum it up, in practice, what you will be doing in search is probably start with word models, not in the vector space models. Just focus on words, focus on what would be the right normalization for those words, and how to what fields to use and how to boost them correctly, and whether to use phrases. So this is what you'll be doing. But my advice to you is, from day one, think very clearly about how you're going to measure what your search is, how your search is performing. Attach more than just one kind of judgment and feedback loop. So, for example, make sure that you have a way to measure conversion rates if you're in e-commerce, or click rates and click models. So just make sure this is something that's doable today. It requires some work, but it's nothing out of scope and out of the ordinary. Just make sure you measure. Once you measure, you can just make changes to the old school search engineering, but you can do this in a very easy way and confident way, which is way more important. And everything is going to be iterative, because essentially building a good search engine and doing good search relevance engineering is a lot of trade-offs, and even more experimentation and trial and error. So this is how it works. This is how it should work, and make sure that you are doing well with that. Once you are very good at measuring your progress and making sure that everything is working, and you are confident in changes that you're making, then you can start introducing things like learning to rank and automating that a bit more, and basically leaning a bit about machine learning and automatic or automated processes that will make those decisions for you. But I don't think this is something that you should start doing from day one. Those areas are still being researched and experimented in. It works and it works nicely, but it is still too big of a leap to make, in my opinion. So this was me. I'm talking about search engineering and what search really is, and how you should take search, and how you should probably also apply this to whatever project and whatever search system you have today. So I'll open for questions now. It's been a bit longer than what I thought it would be. So I'll open for some questions now. If you have any question on that topic, feel free to just put them here in the chat, in the YouTube stream that you're currently watching. You can also approach us privately, and we can take this from there as well. All right, so someone asks me here about entity extraction. And I should say this: entity extraction can use a lot of the things that we've just discussed. So, like I said, for example, dense vectors and BERT and all of those algorithms, the whole point of them is finding what we often call collocations and word embeddings. So you can use a lot of the mechanisms, also bag of words. You can use a lot of the mechanisms to do entity extraction. On its own, it's cool. I think it can also be very beneficial to think about entity extraction of texts as a way of unstructuring the unstructured. So taking those texts that you build a search engine to work on, and which is unstructured, and putting some structure into that. And you do this basically, if you do entity extraction, it is more like, is very likely like doing some sort of a tagging, right? So finding those specific things that you know that you're looking for, and then applying them to a field that is actually structured and semantic. So using entity extraction, you can actually even improve searches, and that is something we've been doing in several occasions. So yeah, this actually also can relate to search, if that makes sense. Oh, by the way, a lot of the time you can also look at what I mentioned, like search logs and click streams, and figure out a mapping essentially between the query strings that people are searching for. So query strings and queries that people are typing in, and what actually happened after the search. So you can see that they searched for something, and essentially they went into some page. So you can look at the page title and the page text, and you can log the search terms and the page content, and then in an offline process take all of those tuples essentially and do something with it. So you can think of this as you know, as a word embeddings problem, right? So you can figure out what words relate to what words, and essentially just maybe even do some sort of hard links between some search terms to some pages, and or boost some words in cases people are searching for that. So that's also something you can do. Also, again, completely valid search engineering, and this is maybe poor man's word embeddings. Again, if there's any questions, put them in the chat window. I have only one more question someone is asking here about n-grams. So n-grams is also a way of executing searches. It's also a way to sometimes bypass a lot of complexity, because n-grams allow you to overcome misspellings and stemmings of complex languages and things like that. But engrams, we talked about precision and recall. So engrams will completely ruin precision. They will make sure that your recall stays low, but your precision, in our experience, is going to be ruined compared to what you could have achieved without engrams and using proper search engineering practices. It's still useful for using for building did you mean kind of functionalities, because engrams are very useful in finding possible alternative spellings for words, at least in most languages. But again, not something I would use for mainline search, like I wouldn't have used fuzziness, fuzzy queries on the get-go for searches. All right, I see there's no more questions, so we'll stop this here. Thank you very much for joining us today or watching this after the fact. Feel free to reach out to us. Check our blog for much more interesting content, and future AMAs are also available, and there is the link over here, as well as past Ask Me Anything sessions. And feel free to propose topics to us, and you can again find that the way to do that in the link for the Ask Me Anything sessions. Thank you very much, and see you next time, I hope.